Hi, I'm Zach Metzner.
And I'm Chris Omering, and we're students in Chris Cunning's honors physics class.
Today we find force, work, and power needed to pull a sled with different amount of weights on it.
We wanted to do this to see if weight variation significantly affects the work, power, and force. And if you look down yonder, you can see how we set up the IOLab to the sled.
We put the weights on the back of the sled. We taped the IOLab to the center of it with the X direction facing that way, and then we put the rope between the two handles, and then we pulled it forward.
Our hypothesis is that the third pole will have the most work needed to pull it. However, the power will be the least for the third pole as well.
This is the free body diagram we used for each of the trials, since the trials were exactly the same, even with the pulling angle. The only variation would be the mass of the sled. For the first pull, we decided to take the average acceleration, and we found the average acceleration by using this region here, because that's when the sled was in motion, and we subtracted it by the average acceleration of this region here, because that's when the sled was at rest. And we decided to subtract them because the IOLab wasn't zeroed, so that was our way of zeroing the IOLab and getting a more accurate acceleration. And we can also find the time that the sled was in motion by taking this region.
To find the acceleration, we took the average acceleration from this area right here, from when the sled was being pulled, and we subtracted it from when the sled was at rest here, because it was not exactly at zero. We also found the time that was needed in this area too, which was 6.96 seconds, and the acceleration was also 0.72 meters per second squared.
For the third pull, we took the average acceleration of this region here. We could also find the time, because this is when the sled was in motion, and we again subtracted that average acceleration by this average acceleration to find the zeroed out more accurate acceleration.
To find the force applied to the sled, we took force applied cos 44 minus the coefficient of friction, weight force minus force applied sin of 44 equals ma. We in then turn figured out that the force applied was equal to 40.8 newtons for pull number 1. We then figured out that the work of the pull was 232 joules, and then the power of pull number 1 was 42.1 joules.
For the second pull, we got the applied force to be 53.6 newtons, the work done to be 306 joules, and the power to be 44 joules. For the third pull, we got the applied force to be 55.6 newtons, the work done to be 317 joules, and the power done to be 41.3 joules.
Our hypothesis was correct because the third sled had the most work to be able to pull it. Our hypothesis was also correct, with the power being the lowest on pole number 3. Since power equals work over time, the more time needed to pull the sled equals the less amount of power to pull it.